But today we are discussing about simple microscope and we have completed the derivational part of that one. Now today our topic is compound microscope. Compound microscope. In compound microscope, two lenses are there. First one is objective. First one is what? Objective lens. An objective lens facing object. If this is the object, this is the principal axis. The lens is here. The lens should be small aperture and small focus. This is known as the objective lens. What is the characteristics of this lens? Small aperture and small focal length. Small aperture and small focal length. Small focal length. Focal length. This is the characteristics of this objective lens. Why? Because the object is already very small. And this is the focus point of objective lens. This is the 2f of objective lens. We have to keep the object between 2f and FO. FO is focus point of objective lens. Focus point of objective lens. But what happened when the object is placed just between 2f and f, but close to f? What happened if this is object AB? Parallel rays passes through the lens, and you know paraxial rays passes through the focus point. This is FO, this is 2FO. This rays will pass through the focus point, and the rays which is passing through the center. Rays which is passing through the center. This ray will not deviate and it will cut here. It will cut here. Now, the image forms here. A dash, B dash. Beyond 2FO. It means FO, 2FO, beyond 2FO. Behind the lens. This is a real image. Now, compound microscope first we will discuss during normal adjustment. During normal adjustment. Normal adjustment. You know, during normal adjustment, our ciliary muscles becomes relaxed and final image forms at infinity. Now see here, if this is objective lens and object is kept in front of this lens between 2FO and FO. FO is object focus point of objective lens. Now the image forms behind the lens and this image is real and magnified. Now you see here, if this point, the point where the image formed lies on the focus point of eyepiece. This is eyepiece lens, is lies on the focus point of eyepiece. Here eyepiece is there. Eyepiece should be relatively larger focal length. This is eyepiece. Eyepiece. What is the characteristics of this lens? Comparatively, it means compared to objective lens, comparatively, upper large focal length. Large focal length. This is the characteristics. Now see here where the image will form. See here, parallel rays passes through the focus point of this objective lens, and the rays which is passing through the center. You see that these two rays, refracted ray will be parallel. These two refracted ray will be parallel. See here. This is eyepiece lens because you are keeping your eyes here. You are keeping your eyes here. and from here you are observing the image, final image. Inside your eyes, these two rays are coming parallel. So you will see this object where parallel is coming from infinity. So you will see the image, final image at infinity, final image at infinity. So we have already discussed that during normal adjustment, during normal adjustment, our ciliary muscles remain relaxed. And this is the fact that when we are observing any body which is lies near to us, then our ciliary muscles becomes more tense one, more contracted. And that's why there is more stress is there over the ciliary muscles. But what happened when we are moving the object away from our eye, then it becomes easier for our ciliary muscles to focus because the ciliary muscles contract less. And when the object is at infinity, then the light which is coming from the infinity are parallel. To convert that light on retina, the ciliary muscles have to contract very less amount, and the minimum stress is there on our ciliary muscles. And we can see that, and we say this condition is called norm. Similarly, this condition when took place inside microscope, compound microscope, this condition is called normal adjustment, where final image forms at infinity. I have already discussed in the previous class that during fine adjustment, final image forms at D, that is 25 centimeter, D for least distance of distinct vision. Now you see here, you know this angle and this angle, you see here. You know, in compound microscope, two lenses are used and the magnification are always multiplied, are also always multiplied. So here since two lenses are used, here how many lenses are used? Two lenses are used. So total magnification produced by these two lenses will be the total magnification produced by the compound microscope. This will be the product of magnification produced by the objective lens into magnification always multiply into magnification produced by the eyepiece lens. Now you see here, you know in lens, what is the formula for magnification? V by U. Just like in mirror, what is the magnification formula? Minus V by U. In lens, it is V by U plus V by U. So this distance we treat at image distance for this magnification produced by objective. In lens, magnification formula is image distance by object distance. But in mirror, here minus sign is there. In lens, V by U. What is the object distance? VO. This distance we represent as VO. And this distance as UO, object distance from the objective lens. So here formula will be VO upon UO. Now you see here U is minus and V is plus for this lens. For this lens, V is positive and its image distance is positive and object distance is negative. So minus sign will be there. Now for eyepiece, I have already discussed with you that during normal adjustment, the magnification formula is D by FE. In the previous class, we have already discussed. So this is the total magnification formula for compound microscope. This is the magnification formula for compound VO by UO into D by FE. Now you see here, one of the most important case of magnification in compound microscope, that is maximum magnification. See here beta, here the role which is the most important role in compound microscope is played by the objective lens. By whom? By objective lens. So write down, for maximum magnification, see here beta, as we are moving the object towards the focus, the image goes on shift, moving away. And the size of the image goes on increasing. Size of the image goes on increasing. When we are moving this object close to the focus point, close to the focus point, then where the image forms? The image forms near the eyepiece lens. So the image distance can be treated as total length of compound microscope tube of compound microscope. So right here, during maximum magnification, during maximum magnification, during maximum magnification, this formula becomes, magnification of compound microscope formula becomes here, image distance is equals to length of the compound microscope, because when we are moving this object closer to F, the image moves away and it forms just close to this. That's why this total distance, the distance between objective lens and an eyepiece lens, is treated as length of telescope. So this is L, image distance L, and this distance is treated as FO. Because when object shift close to F, then image forms at very large distance. But see here, the focus point of this lens, focal length of this lens is very, very small, because the size of the object is microscopic. Now, into D by FE. This is a magnification formula of compound microscope during maximum magnification. Now we will discuss about compound microscope during fine adjustment. See here beta, during fine adjustment, final image form during fine adjustment. Final image forms at D. Final image forms at D. Forms at D. D means 25 centimeter. Now you see here, see the ray diagram. This is the objective lens, small aperture, small focal length. This is the principal axis. But the ray diagram is very important. This is the focus point of objective lens. You have to keep object just close to F. Now, this is object AB. This is FO. Focus point of objective, and double of focus point is 2FO. Where the image form? Parallel rays passes through the focus. The rays which is passing through the optical center. This point is known as optical center. It will remain undeviate. Moves in a straight line. Image forms here. A dash, B dash, inverted image. And now, if you are moving the eyepiece lens closer towards the image which is formed by the objective lens, what happened? See here, once again, we have placed that object in front of this objective lens close to F, but between F and 2F. F and 2F. Its real image will be formed beyond 2F and it is magnified, real one. Now, if you move the eyepiece lens closer towards this in such a way that final image, what is this distance? UP, object distance from eyepiece. So that final focus length is somewhere like this. Its focal length of eyepiece shift here. In the previous case, we have moved this lens. When we have moved this lens apart from this object, its focus length here, its focus length of eyepiece start to shift, and during normal adjustment, the focus point lies here. The image formed by objective forms on the focus point of eyepiece. But during fine adjustment, what we do, we move this objective lens close to this object. So what happened? Focus point keeps on shifting, and there is a certain distance where the final image formed by this eyepiece lens forms at D, that is 25 centimeter. But how the image form? Parallel rays passes through the focus point. The rays which is passing through the center, moves in a straight line, moves in a passing through the center, moves in a straight line. Now these two rays, if you produce it backward, they will cut where? They will cut here. And the image formed is highly magnified. This distance is D. From eyepiece. 25 centimeter. D means what? 25 centimeter. See here, once again. When the image formed by objective lens comes within the focus point, that is between the focus point of eyepiece lens and optical center, then in such a way that final image forms where? Final image forms at infinity. See here, beta. Really, these two refracted rays after refraction start to move away, so they will never intersect. But if you produce them backward, the final image forms where? This one is the virtual image, and this is inverted. The final image forms at D, this distance of distinct vision. From here, you are observing the final image. Here, the position of your eye will be here. Now you see here, for fine adjustment, during fine adjustment, what is the formula for magnification produced by eyepiece? We have discussed one. So total magnification is equals to total magnification of compound microscope will be the product of magnification produced by the objective into magnification produced by the eyepiece. Here, this distance is again VO and this distance is UO. O for objective lens. So image distance from objective lens upon object distance of objective lens. Minus sign will be there because this one is negative, this one is positive, into what is the formula for magnification that is produced during the fine adjustment? 1 plus D upon FE. This is the formula for magnification. Produced by the compound microscope during fine adjustment. See here, beta, again for maximum magnification, image distance will be L and this will be close to F, that is FO. The position of this final image, how will it represent? A double dash, because the image formed by the objective is A dash, B dash. Final image is represented A double dash, B double dash. And where it is formed? At distance capital D. And now this is the final formula for magnification produced by the compound microscope. See here, beta, prism is a refracting medium which have two refracting surfaces. This is known as A, BC. BC is known as the base of prism. This is known as base of prism. These two are refracting surfaces. This is first refracting surface and this one is the second refracting surface. And this angle is known as angle of prism. A को क्या बोलते हैं बेटा? A is known as angle of prism or refracting angle of prism. Refracting angle of prism. But see here, we will discuss about the minimum deviation case. That is when the refracted ray passing through the prism, it becomes parallel to the base of prism. बेटा देखिए, when you will draw, see here बेटा, when we pass, this is normal, angle of incidence like this, angle of incidence like this, angle of incidence like this, goes on increasing the angle of incidence, and with the angle of deviation, you will get a graph like this. So this is angle of deviation and angle of incidence. There is a certain angle at which angle of deviation becomes a minimum. This angle is called minimum angle of deviation. During minimum angle of deviation, the refracted ray passes parallel to the base of the prism. Minimum angle of deviation cases. So we are just here deriving the formula for minimum angle of deviation when the refracted ray becomes parallel to the base of the prism. Prism during minimum angle of deviation. During minimum angle of deviation. But this is very important derivations for a graph that you should know, and this is practical one of the experiments that you have to perform in lab activity. Minimum angle of deviation. I will explain this. Minimum angle of deviation. Minimum angle of deviation. Delta for deviation and m. Minimum angle of deviation. So you see this. Let us see here. This is prism. Lit a monochromatic light. Mono means one, chroma means color. Single wavelength light. This is normal. N1. So if this is a monochromatic light, monochromatic light. But I used to know that refractive index of any medium is inversely proportional to wavelength. Refractive index of any medium is inversely proportional to wavelength. You know this color. ROYGBIV, Vivio. But this have maximum wavelength. So for red color, which have maximum wavelength, the refractive index offered by this prism will be minimum. You know this formula, sin I upon sin R is equals to mu. See here, beta. As we are increasing the angle, sin R increases. And at 90 degrees, the value of sin will be maximum. Now you see here. Here the wavelength is maximum for red light, so minimum refractive index. And minimum means R will be maximum. R will be maximum for red light. This will go straight. If this is not monochromatic, single wavelength not there, if it is white light, that is compared 7 colors, then the minimum wavelength will be of violet color and maximum wavelength will be of red color. See here, beta. Maximum angle of refraction. This is normal. This is incident ray. This is refracted ray. This is angle of incidence. See here, beta. This ray should go straight, but it will not go straight because since the light is moving from air to glass, so it will bend towards the normal. You know that violet color have minimum wavelength, so refractive index that is provided by the material of the prism will be maximum. If wavelength is minimum, refractive index will be maximum. And when mu will be maximum, R will be minimum. That's why R for violet color is minimum. And similarly for all the 7 colors, R, O, Y, G, B, I, V. And that's why all the light, all the different colors of light get separated. We will discuss about this term later on, but here we are taking the only the monochromatic light. You should know this formula. This is known as, I will explain the Cauchy's equation. That is very important part of your this prism. Very important part. Now you see here, this is monochromatic light. So only single wavelength is there. So what happened? You see here, this light should go straight. But what happened? Since this is denser medium, so speed of this light will decrease, so it will bend towards the normal. This is the case of minimum deviation. So refracted ray will be parallel to the base of the prism. You write here, in case of minimum deviation, the refracted ray becomes, in case of minimum deviation, that is, light passes symmetrically through the prism. Symmetrically means the refracted ray will be parallel to the base of the prism. In case of minimum angle of deviation, minimum angle of deviation, the refracted ray will be parallel to the base of prism, to the base of prism, base of prism. Now you see here, again you draw normal here. This is second normal N2. So this ray should move straight, but it will not move straight because the light is coming from glass to air. Air is rarer medium. So speed of light will increase and this light will move away from the normal like this. Now you see here, this is called emergent ray, this is refracted, this is incident ray. Incident ray should go straight, but after passing through the prism, it is moving like this, emergent ray. Now if you produce it backward, you can say that this is the angle of deviation. This light should go straight, but when you are placing a prism in its path, the light gets deviated by how much angle? This is the original path, but after passing through this light, this gets deviated by this angle. How much angle? How much angle? This angle is called angle of deviation, delta. This is called delta, angle of deviation. You let this be P, this is Q, and this be R. Angle PQR is called delta. Angle PQR is called delta. Angle PQR is called angle of deviation. Called angle of deviation. Now you see here, but all of you see, let this be R1. First refraction. The angle made by refracted ray with the normal is called angle of R1. And this is called angle of incidence over the second surface. Let me treat this angle be, we are referring this angle as R2 and this angle as E. Now all of you see, in case of minimum angle of deviation, R1 will be equals to R2. Why? Because since this ray is passing parallel to the base of the prism, this is parallel to this, then this angle will be equals to this angle. This angle is what? 90 degree. This angle is what? 90 degree. Why? Because this one is normal. And this whole is equals to this. So definitely R1 will be equals to R2 because sine I upon R is equal to mu. You see this formula. For this is A, this is B, this is C. For side AB, for refraction through first surface, for refraction through first surface. For Refraction through first surface. First surface. बेटा ये